In this lecture, we talk about basic data structure, which is called a stack. Usually, in our daily life, we used to observe the stacking of items, where the specialty of this is we can keep on place the elements or the objects on top of the existing stack, and we can remove the element only from the top. So, taking this as a cue, data can also be processed in the similar fashion whenever such kind of requirements are existing. So this is called last in first out type of operation, where the last object which enter the structure will leave first. So data objects will be stacked here. To observe the current location or current status of the stack, we used to have a variable which is called top, which refers to the which keeps track of the number of elements present in the stack. So this can be implemented in several ways. Here we talk about implementation of stacks using arrays. Every array can also be treated as a stack, where the entry of the elements or insertions of the elements and deletion of the elements will take place only from one end. The other end will be kept fixed. We don't do any kind of operations on the other end, from the other end. And initially we initialize an array with top variable. A variable is declared top, which is where which indicates the size of the stack. So initially we start with top as -1, which indicates the stack is empty. Abstract data type of stacks, what are the operations that we can perform on the stack is we can check whether the stack is full or not. We can check whether the stack is empty or not. And we can push an item. The operation of insertion is called push here. We can push an item into the stack, and we can delete one of the items. We call it as pop. So by default, the topmost element will be deleted. So we call it as a pop operation. And also peek, this is used to get the topmost element of the stack. Whatever topmost element is existing, we can get it. That operation is called peek. And we can also have the current size of the stack can also be obtained. These are the primitive operations that we can perform on stack, but of course combinations of these things will result in variety of operations on stacks can be visualized. So here, for the sake of understanding, stack is visualized here. In the first position, the top is taken as -1. When the first element is inserted as 100, then top becomes 0. So the first element is inserted. Here, if you look at the array is consisting of 4 elements. So 0, 1, 2, 3 are the locations of the array actually. But top is a variable which indicates the current size of the stack. So initially when 100 is entered, the top is taken as 0, and 200 is entered, top will be incremented to 1, 300 is incremented, top will be incremented as 2, and when 600, the topmost element is inserted, then top will take the value of 3. So once top is equal to 3 and the size of the array is 4, so it's an indication that the stack is full. At this stage, if we want to enter one more element, we can't do that because there is no space for that. So here top is equal to 3, size of the capacity of the stack is 4, so we can't enter any element further. Similarly, when I want to delete one element, the element has to be deleted and top variable has to be decreased. This is how the stack operations can be performed. Now let us look into some of the operations that we perform on the stack. The function is full is a function which checks whether the given stack is full or not. So as per the previous slide, when an array is initialized of capacity n, top can take values from 0 to n-1. So once top reaches n-1, it's an indication that the stack is full. So we'll check that condition, that top plus 1, top is equal to n-1 actually. So top plus 1 is equal to length of the stack, or if we are using an array for this, size of the array. If it reaches equals to that, at this stage we cannot enter or we cannot insert one more element, then we can return that the stack is full. So the condition is top plus 1 is equal to length of the stack is the condition. Here again, by default top will be taken as -1 when the stack is empty, and size of the stack capacity of the stack is n. In that case, top plus 1 is equal to capacity of the stack is compared. Similarly, E is empty is another condition. Here you can compare either top is equal to minus 1 or top plus 1 is equal to 0. Any of the conditions can be used here. If I use top plus 1 is equal to 0, that means top is equal to minus 1, which indicates no element is present in the array or the corresponding stack. If we implement stack using array, so no element is present in the stack, it's an indication that the stack is empty. Similarly, if you want to get the peak, again, peak is indicating the topmost element. Again, by default, if top is equal to minus 1, no element is present. So in that case, stack is, we have to give the answer as stack is empty. Otherwise, whatever element is present in the location of top, because top is a variable which is indicating the location of the topmost element. It's not, top is not the element, but the location of the element in the stack. So the element present at the location top, so that is why stack of top is taken here. So whatever be the element or object that is present in the location top will be returned, and that gives the topmost element in the stack that returns the value. So peak is such a function which returns the topmost value that is present on the stack. Look into the two important operations of push and pop here. If you want to push an item onto the stack, we call it as push, and first we check whether the stack is full or not. Just like in the previous slide, here we check whether top plus 1 is equal to length of the stack. If length of the stack is n and top will be equal to n minus 1, that's an indication that the underlying structure is full, already filled with the objects. So top plus 1 is equal to length of the stack, then we return stack is full. Otherwise, then what do is we'll increment the location top to top plus 1. So whatever the current top is indicating, we increment that top to top plus 1, and at that location we push the item into the stack. So how do we push? Stack of top is equal to item. So we insert the data in item into the location which is updated as top plus 1. So stack of top is taken as item. So now the current top indicates incremented one. Already item is inserted and top is incremented. This is how the operations are performed for a push. And when it comes to the pop, again, pop can be performed only when there are items in the stack. If by chance a stack is empty, we cannot perform the pop operation. So first we check whether top is equal to minus 1 or not. If top is equal to minus 1, it's an indication that the stack is empty and we cannot pop out any element from this. So if top is equal to minus 1, print stack is empty and just come out. Else, if it is not the case, then the current top has to be lowered because we are deleting one of the items. So the current top has to be lowered by 1. Top is equal to top minus 1, and the whatever the element that is present at top plus 1, stack of top plus 1 is returned. So whatever element is to be deleted, that will be deleted because top is already lowered. So whatever element is present at top plus 1 is the element to be deleted. So delete stack of top plus 1, and already the current top is lowered. So for the next operation, the current top will be already updated, top minus 1. So this is the topmost element is deleted from the stack. Again, several variations are there. We can implement the same thing in several ways. This is just I'm presenting one of the ways. This is not the only way to present the operations. This is one way. For the benefit of understanding, just I'm presenting an example here. In the first instance, top is equal to indicating minus 1. Once stack is empty, then if you push a data object a onto the stack, so if you perform an operation push, top will become 0. So item is pushed, top becomes 0. If you push one more item b, then top becomes 1 and push element is inserted. Like this, push c, again top will be incremented to 2, push d, top it will be incremented to 3. Again, if you want to push one more element at this stage, top will be incremented to 4. So here by this time 5 elements are inserted, A, B, C, D, E, and capacity of the stack is full because the underlying array is already full. So no more element can be inserted here. So how do we check this? Top is equal to 4 and length of the stack is 5. So top plus 1, 4 plus 1 is equal to 5 is indicating that the stack is full. So this is a full condition. Again, if you want to pop out one element, whatever topmost element is there, that has to be popped out. If you look at the operations, in case of push, we are indicating the element. In case of pop, we need not specify any element because by default the topmost element will be popped out. So if we perform pop operation at this stage, E will be popped out and top will be reduced by 1. So previously top is equal to 4, now pop will be reduced by 1, top becomes 3. So if you perform one more operation, top will become 2 and D will be popped out. Like this, if we keep on pop out the elements at a stage where all the elements are popped out and top becomes -1. So this is the stack empty condition. At this stage, if you want to perform one more pop operation, top plus 1 is equal to 0 or top is equal to -1, which indicates that the stack is empty and you cannot pop out any element. Some of the complex operations that we can perform using stacks also. Reversing a stack, whatever elements are there in the stack, if we want to reverse them, we can use auxiliary data structures and we can reverse the elements in the stack. And similarly, can we sort the elements of the stack? Already we have seen sorting algorithms. Can we implement all these sorting algorithms on the stack? A quick sort, mid sort, bubble sort, whatever sorting algorithms we have seen that they can be implemented on the stack. Similarly, we can implement queues, another data structure, of course, using stacks. And there is a notations or postfix, prefix, and infix notations for arithmetic expressions. We can also evaluate those expressions using the stacks. Similarly, whenever parenthesis matching, whenever large expressions are there involving several nested parentheses, whether the formula is perfectly indicated or not, or balancing is done or not, can be checked, or parenthesis balancing can be checked using stack again. Similarly, another operation is given an element, what is the next greatest element in the stack? Similarly, what is a minimum element in the stack at any point of time? What is a minimum element of the stack? At any point of time, what is the maximum element of the stack can also be identified. We can write programs for this. They will be used in several applications. They can be used in several applications. Similarly, towers of Hanai problem can also be solved using stack and expression conversions from infix to postfix and postfix to infix, of course. And in graph theory, directed acyclic graphs, we can use BFS and DFS. Implementation of BFS and DFS can be done, breadth first search and depth first search can be done using stack operations. These are some of the operations that we can use in applications. Similarly, when it comes to practical applications, simplifying paths in a file system can be done using stacks actually. Given an absolute path for a file in a unique style of file system, this can be simplified using stack to handle parent directory references and unnecessary parts. We can remove them and we can use a stack to simplify the file paths. Similarly, expression parsing and validation. In case of programming languages, whenever expressions are given using a stack, actually we can parse and validate the expressions in programming languages. The other one is web browsing. If we keep on browsing the pages, if we go back, actually we have to remember the sequence in which we have traced the pages. So stack can also be effectively used there for such kind of operations. These are some of the operations of stacks in applications.